Yeah. Sometimes it's like that. Okay. Gradually, we are coming to the end of the semester. We started not long ago. So you realize that everything is about starting. The end will come soon. So today we are treating our last topic for the semester. Can you see my slide? Can you see my slide?
Yes, we can.
Hmm.
Yes, I can. Maybe I don't know for others, but
But everybody's quiet. Nobody's talking. Sir Bernard,
Yes, sir. We can see it.
I believe you are doing well.
Yes, sir.
Okay, I'm also doing well. So we are treating light and optics today. So basically, what are we talking about? We know that light is electromagnetic radiation that carries energy from one source to observers, and is critical subject of optics. So when we are talking about optics, we are talking about light. So optics is the branch of physics that study how light behaves, interacts with matter, and forms image. Why light is important? Why light is important for everyday life? Why do you think light is important? Do you believe that light is important? Why do you believe so?
Yes, sir, it is.
Yes.
So
What is
it helps
important?
us to see.
It does what?
It helps us to see.
All right. Without that, you'll be in darkness. It's the light that is helping you to see. Yes. Who else? How important is light?
let's say
Yes.
so the light helps our vision.
Good. That is true. And the food that we eat, basic elementary school, we were taught that without the sunlight, plants cannot produce their food. So light is part or plants need lights to produce their food through a process we call photosynthesis. Is the driving force in that process. Without the lights, you can't take photographs. You can't take photographs in darkness. Can't watch TV, computer screen. You can't see anything. So light is the driver of what we see. But what do you observe? On the properties of lights. You know, a time that you see the sky looks a bit blue or a bit red when the sun is about to set. What caused that? Have you observed the blue sky? Do you normally observe when the sun is about to set? All this are caused by the scattering of the sunlight by the air molecules. That gave the cloud looks blue. The sun looks a bit red when it's about to set. The scattering of the sunlight that gave you different colors that you observe. Your mirrors that you use. Why? How do you see your image in the mirror? It's lights, reflection. It's a property of lights. Reflection of light that made you see yourself in the mirror. Without the reflection, that property, you can't see yourself in the mirror. Glasses and contact lens. You observe that the light from the environment is what is entering into your eye, and the glass is helping to focus it at the retina. So that's the purpose of it. The light from the environment entering into your eye for you to see. It needs to be focused at the spots, the retina. So glasses and contact lenses, that's their basic work. You observe rainbows, the atmosphere. It comes to the separation of colors, which you normally call dispersion. Separation of colors, like when you're using your prism for your experiments, you're able to experience, observe this kind of separation of colors. So that is what happens when anytime you observe rainbows when it's about to rain. Why is it that mostly when it's raining, when it's about to rain, there must be water droplets. There must be raindrops before you can observe it. So that's what causes the scattering, the separations of the colors. So as they bend in the red drops, so that's what makes the rainbows shows the colors. Yes, those who have taken the aircrafts, they are on board. Sometimes you observe the rings around the plane shadow. All this is about the interference of light. So these are some of the properties of light that we observe every day. Every day you see one or the other. This tells you the presence of light. Without light, you are dark. The lights of the whole body through the eye. So if you don't have eye, the whole thing becomes dark because light cannot enter. Yes, we were told that light has a dual nature. Light can behave like a wave at a point in some experiments, and like a particle in the other. Do you remember lights behaving like a wave? Can you give an example where the lights behave like a wave? SHS experiments.
So when a level a light travel on a crooked surface.
Okay. Okay. All right, who else? So about light travel as a particle. Light travel as a wave, light travel as a particle. Do you remember any example? SHS experiments. SHS experiments. Linear propagation of light. After that experiment, the experiment that it shows that light travel in a straight line. Now you put a light and you go to the other side to observe the three arrangement. When you shift one, you cannot see the lights. When they are all in alignment, you can observe the light from the other side. You have not done that experiment, SHS. Oh, okay. All right.
So we did it, sir.
You have done it?
Yes, sir.
Oh,
But the
great.
understanding wasn't clear.
Oh, just to know light, to observe that if there's no alignment, you will not see the light from the other end. But when they are all in line, you can observe the lights passing through. But when there's a shift, the light will not burn. The light is not like water that will find its way, no matter what you put on its way. But when you block it, it produces a shadow at the other end. It will not force its way through, like water. So the model, light behaves like a wave. You know, Newton's favored particle, and explain reflection and refraction with it. So refraction and refraction. So in the 17th to the 18th century, Christian which argued that light is a wave. And 1801, Thomas Young demonstrated the interference, a hallmark of wave behavior. And the almighty Maxwell showed that light is a high frequency electromagnetic waves. And Hess confirmed these experiments in 1887. So mostly as a scientist, you discovered anything, you put a procedure down, another scientist will go through the same procedure to confirm your work. And sometimes, if it works, they give your name. So any of the units that we see is the name of those people who have discovered that procedure. There's nothing new though, but because you were able to explain it to everybody, you get an award for that. So light travel as a wave that we talk about reflection and refraction. So when a light travel as a particle, so we are trying to know about photoelectric effects. So what is photoelectric effects? Do you remember photoelectric effects? What is this? Photoelectric effects. Photoelectric effects. All right, photoelectric effects. Basically, we are just talking about if the light is having an energy to eject electrons from the metal. So that is what Maxwell describes as photoelectric effects. But you realize that this process could not be explained by the waves equation. So electron kinetic energy depends on the frequency, not light intensity. That's what Maxwell said. The electron kinetic energy depends on frequency, but not the light intensity. Yes, Kingsley.
So please, the photoelectric effect, is it the sun reflecting, for example, like the sun reflecting on a roofing sheet?
Yeah,
Then
photoelectric. Yes.
then the brightness of the sheet will like be choking your eye or something like that. Is it that one?
Yeah, so when we say that the effect took place, what it means is that the sunlight has enough energy to remove electron from, let's say, the iron sheets that you are looking at. Yes, so you could observe that kind of reflection from afar. Is that not so? Hello?
Hello. Yes, sir.
So for photoelectric effects to occur, there must be a minimum frequency below which no electrons were ejected. So Einstein explained it by treating the light as a stream of particles. So each energy is having, that's what we have, the energy is equal to the Planck constant, that's the H, and the frequency. So the Planck constant value is 6.63 times 10 to the power minus 4 joules seconds. So this is the energy that we know, S times. So you can use wavelength here. If you are using wavelength, how does wavelength relate to frequency? How does wavelength relate to frequency? Can you rewrite this equation using the wavelength? How does the wavelength relate to frequency? What's the relationship between wavelength and frequency? You don't remember your physics, eh? So basically, lights behave like a waves where you see the interference or diffraction. Light behave like a particle. So when you observe the photoelectric effects, and then you are using the photon model, the conclusion is that light is both either a particle or a wave. You choose which one you want to use in your experiments. That is light. So if you want to talk about the geometric optics assume light travels in a straight line. So we focus on the reflection, refraction, dispersion, and total internal reflection. So when we say reflection, what are we talking about? If we say reflection, what are we
when
talking about?
something bounces back, or
I didn't hear you. Engineer Philip,
yeah.
I didn't hear you.
Okay, sir. So when a light fall on a smooth surface and
What happened when the light fall on a smooth surface?
and bounce back,
Okay. Now what's the law of reflection? What the law of reflection says?
So please, the law of reflection says the angle of an incidence is equal to angle of reflection, both
Great.
measured from the normal to the surface.
Great. What about the second one? The second one? You don't remember? So when we say refraction, what are we talking about? When we say refraction, what are we talking about? Refraction of a light. What are we talking about?
So refraction is when light bend away from the normal.
I didn't hear you, sir.
So it is the bending away of light from the normal.
Okay. What caused the bending? What caused the bending of the lines?
So I guess the densities of the particles or materials involved.
Great. Good opinion. Any other opinion? What caused the bending of the lines?
So let me try.
Hello.
I'm
Oh,
listening.
So,
so
sir, I
hello.
think
Please, can you hear me?
the change
Philip,
in
Philip,
speed.
Philip,
Uh,
let's allow the lady to talk.
Okay, so for example, when there's a straw in a glass of water, it's going to look broken from the outside because uh, the light is going to bend as it leaves the water and enters the air. So in this instance, you can say that there is a change in speed that causes the light to change direction or bend or show as though it's bent. So the speed is affected, and we know light travels in a straight line. So
All right. Great opinion. You are relating it to everyday life. That's good. Good to hear from you. Philip, anything to add? Philip, anything to add? Engineer Philip, are you off?
okay, sir. So, I think it depends on the density. So, the change in the speed of the wave as it passes at an angle. So, from one material into another with a different optical density.
Oh, yes. I think all of you said what is expected. And when I'm marking, I think everybody will get equal marks. Basically, what everybody is expressing is that the light must move between two mediums. Most of the time, it moves from the less dense medium into the high dense medium, like air to water. So the refractive index of water is higher than that of air, or from air to glass. The refractive index of glass is higher than that of water. Air is 1. Refractive index for glass is 1.5. So as you are moving from less dense medium to a high dense medium, the speed at which you are moving will reduce, will slow down. But like you are running on the earth and you enter into a water, your speed will reduce. If you play in water before when you were swimming, you realize that there's some kind of friction in the water that will slow your movements. So basically, that is what is happening. You are going, and then it slows your movement. So you bend towards the normal. So basically, refraction, as Yaira was explaining, when you have either your spoon or egg or anything that you put in there, when you see the reflection that the thing looks a bit bent. So it depends. What it means that the movement of the light has entered to a different medium or entered to a different density, which is higher than where it was. So it helps to bend. So there are two things I'm looking for. Two media with different densities. Different densities. Could be from air to glass or air to water. And second, it reduces the velocity or the speed at which it was moving. That caused it to bend. Are we together? Are we together?
Yes,
Yes,
sir.
sir.
Yes, because sometimes the line will be cutting. So if I'm not hearing your voice, to be sure that I'm not talking to myself. All right, so you see that from this write-up, I've written air to water or air to glass. So the Snell's law, remember that law? It says what? What did the law say? So in essence, I want to ask you what is Snell's law? You write the formula for me. All right, dispersion.
So,
Yes.
so for the next law, can I say it's the ratio of the like from the formula you wrote? I'll use that one to explain the Snell's law. Ratio of the angle of incidence to angle of refraction.
The sine of the angle.
Yes, sir.
Yeah, the formula is the sine of the angle. Okay. You have to understand this so that you can explain. It's just a matter of explaining what is happening. So if we talk about dispersion, what's your understanding? I hope you have done that experiment, the prism experiment.
Okay, sir. So dispersion of light waves is when light falls on a surface and the light ray, I mean, spread to different angles to trying to remember this thing. To multiple angles.
Okay. That's great. That's true. That's great. All right. Dispersion. As we use the prism in our lab to show the separation of the colors. So you realize that different colors of the lights refracts by slightly different amounts. So the colors spread out as we normally observe in the rainbows when it's rainy or about to rain, the cloud. And in our labs, then these are things that we have observed. So I'll speak in details on that. So we talk about total internal reflection. When the light travels from high index medium towards a lower index medium at a large angle of incidence, all lights may reflect back internally instead of refracting out. So this technology is what they use in the optical fibers, or what we normally call fiber optics communication. So as we are talking to me, as we are hearing our voice, there have to be this transmission. So basically, something different is happening here. When we started talking, we talked about the light moving from less dense medium to a high dense medium. But as we talk about the total internal reflection, let me see. Oh, why is this thing? Did I finish? I hope you can see the slide. I hope you can see the slide.
Yes, sir.
All right. So basically what we are trying to say is that light is electromagnetic radiation that transfer energy and information. It's essential for vision. Without light, you can't see. Photosynthesis, without light, plants cannot produce their food. And many modern technologies. Light has a wave and particle duality. That is a fact. It displays interference and diffraction, and also photon-like behavior. So both models are needed. Geometric optics use light as a ray to explain reflection, refraction, dispersion, and total internal reflection, which underline everyday phenomena such as mirror, the lens that we use, while rainbows formed, and optical fibers. So now, measurement of speed of light. It wasn't an easy task. How do you measure the speed of light? Where actually your reaction time is higher. The light, speed of light happen in a flash. And before you react, is gone. How do you measure it? So it's a bit difficult, but Galileo attempted it. Yes, trying to see if I can measure the speed of light. So he did what? Try to use the Latin, two of them, and put them about 10 kilometers apart. Just to see if I can measure the distance this one moved to this place. But unfortunately, he couldn't measure the speed of the lights. Why? Because the time the light is living is much less than the time that you are going to react. The reaction time before you are very conscious to move, the light has passed. So the delay looks instantaneously. So the conclusion will be that you can't measure the speed of light. It's not like you cannot measure, but the method that you are using may not be appropriate for that measurement. So Galileo made the first attempt to measure the speed of light. So after that, another scientist took it up the challenge to see if something can come out of these failed experiments. So Römer used the moons of the Jupiter, especially trying to use the initial whose orbital period is about 42.5 hours. As we know, the Earth orbits the Sun. So the distance between the Earth and the Jupiter changes. So as they move, there will surely be a change. So when the Earth is moving away from the Jupiter, the I-naught eclipse appear later than expected. When I say eclipse, I hope you understand the alignment. When the Earth is approaching the Jupiter, the eclipse appear earlier. So this is about rotation. The moon, Jupiter, rotating around, orbiting around Sun. So Romeo interpreted this shift as due to the extra time light takes to cross the changing Earth-Jupiter distance. So the data that he got estimated 2.3 times 10 to the power 8 meter per second to be the speed of light. And one important thing that came out from that experiment is that it shows that light has finite speed and gave the first descent estimates. So you pick up from nowhere and you're able to make a headway. So somebody will pick up from where you left off. So basically, this is what Romeo is trying to do. You see the Sun, and you see the Earth, and the Jupiter orbiting. So trying to measure the distance that is using to do this. So we have the I-naught, the orbiting. So Romeo meter for the measuring the speed of light. So the time interval during which the Earth travel about 90 degrees around the Sun. So the Jupiter travel only 7.5. So basically, this is what we was trying to explain. This is what he used to be able to come up with something. And then is all able to improve on what others started. So he used a rotating tooth quill, a distant mirror for the first. So successful Earth-based measurement. So he have done the first successful Earth-based measurement when it comes to measuring the speed of light. So the light from the source passes through an opening in the wheel, travel to a mirror for a distance, reflect back. So you're trying to see that the reflection, the light reflect from the mirror and attempt to pass through the exit opening. So the speed is deduced by the 2D, that the distance over the round trip time. That is the time, the round trip for the round trips. So this is what formula that he came out with. So basically, he was able to arrive at 3.1 times 10 raised to the power 8 meters per second. So basically, you realize that this value and the actual value that we know today is very close. 2.99979. This is the value that we use. The cesium. This is from the cesium atom that we use to measure the speed of light. So the value that we got is approximately equal. So that's what's using today. So this is the experiment that he put across. So the tooth bill, and this is the mirror. So able to measure the distance. So that's a very brilliant imagination. Want to measure the speed of light. They are using this to see the light hitting the mirror and reflecting. So able to have the two movement, the 2D. So it hits and come back. So that's the round trip that you can use to measure. So this is the process that you use to measure the speed of light. And then he got it. That's what happens. So basically, this is how he explained what he did. That the field has 360 tips and 360 gaps. So the angular displacement between an opening and the next tip, angular displacement basically 72, 720. So for full revolution. So at 27.5 revolution per second, the wheel's angular speed, the angular speed is 2 pi times 10 to the power 27.5 radian per second. So the time for this small rotation, so you are using the time to measure using this formula, the angular rotation. So you're able to measure this value. And you had the 5.05 times 10 to the power. So this is the time that you have gotten. So after you have gotten the time, you know the 2D of value, you're able to get this value. So you're using the 2D over the time. So this value that you calculated, and it's a bit close, 2.97. So 2.99 or 2.97. That's a good attempt, which is indeed very close to the accepted value of 2.9979. That was a good attempt as a scientist. So approximation of geometry optics. So basically, when we talk about geometry treats light as a ray, not as a wave, as a ray. So it means that light travel in a straight line. So it travels perpendicular to the wave front in a uniform medium. The ray approximation is valid when the wavelength, the lambda, is small compared to the size of the opening or the obstacle. So if you want to approximate the wavelength should be small compared to the size of the opening of the obstacle when you're using cameras. These are the technology that we use in coming out with cameras. Diffraction, spreading of waves through a small opening. So diffraction, basically, waves are spread through a small opening. So when you have this, we are looking at the modern that survive. So this is less than the distance. So we have the lambda. Basically, this is how the waves form to look like the sinusoidal waves. So long as this getting very small. So we have the D as the characteristic diameter. So we are trying to look at the diameter of that wave. Under this discrete condition, light passes through a large opening, continuing to propagate in nearly negligible, nearly straight line. Shadow remain exceptionally sharp and diffraction fairly good. So basically, in this approximation, the light travels in a straight line. So it reflects and refracts at a boundary, which lets us model the mirror. So mostly you write that when the light is moving from one medium to another, there will be reflection, there will be refraction. So the refraction basically means it passes through and bend. And reflection means it goes back, it reflected back when you hit any obstacle, any boundary, moving from one medium to another, moving from air into your eye, there'll be refraction. So basically, that's what is happening. So that's the technology that we use in our eyeglasses, the lenses, the cameras, everything. This is the foundation. That's how mostly when you are starting science, they want you to have this foundation to appreciate what is happening. Though what you are going to do may not necessarily relate to this, but you need to have opinion about how these things happen. That's why we are here. So basically, when the opening size is comparable to the wavelength, diffraction becomes important, and the model fails when the opening size is comparable to the wavelength. Diffraction becomes important in the ray model phase. This is treated as a wave optics. So basically, this is what we want to talk about. So if the lambda is less than the distance, so you see what is happening, the sharp shadows, straight line propagation. So this is what happens, it moves straight. But if it is approximately equal, the wavelength is approximately equal to the distance, the wave spread. So this is what is happening. The wave will spread. So depending on which one that you need, and then you let the wavelength go from your opening, the opening that you have, the diameter of the opening, if you are going to use a camera, the opening that you have, you open for you to take a picture. So the hole there is the measurement that you have to take. So looking at the wavelength of the light that you are using. So if you want it to spread, you know how you design it. So the gap, if the gap is less than the lambda, so the point source spherical waves. So basically, those people who works on cameras, lenses, and all those things, they use this idea to be able to design a perfect fit glass for you, a perfect fit camera, that you can use to take pictures. So camera is in the aperture, and when in all this, use this law, this foundation, these were the basic principle behind them as we use them in our everyday lives. Basically, we are just trying to look at the light, how does it behave if the light is less than the diameter or is equal to the diameter. The opening much smaller than the diameter. So basically what is happening and what is the governing physics, the physics principle behind it. So it's just wanted to take note of. So as you could see clearly here, and looking at the mirror and the prism, so you see the hole that we are measuring, you see where the diameter will be and where the ladder will be. So that is the diameter. So depending on these sizes, so it tells you what exactly that you can measure. So normally they use this in the mirrors and the prisms. So they redirecting the parts. So looking at this as a camera, so you see the face, this is the diameter of the camera that's normally used. You have your opening. So the telescope and cameras capturing distance scales. So this is basically what the technology use designing. So you have your eyeglass. So all distance counts. How big is your eyeglass and the diameter and what light that are entering, the wavelength light that are entering. So this basically the technology that is used. So if you want to go into the manufacturing of all these things, you have to perfect this and get understanding. The typical aperture and element in every the instrument are massive compared to visible light wavelength because that is less than the diameter. Remaining true across all these devices, we can completely ignore wave optical details. So basically, all these ones, you see that. So when you check this one, the size of the wavelength is smaller than the diameter of the one. So this one, you see that this one is very smaller. So most of them, that's what they employ. This is the technology that they employ in using our lenses. Any question? Any opinion? Are you there?
Yes, sir.
Yes, sir.
Great. Great. I can hear your voice. So basically, when you see this, your camera, your mirror, your lenses, and the technology that were employed. But basically, the wavelength is smaller than the diameter of like the opening. What you see here, diameter is smaller. So basically, what we can see here, lens is to be able to deflect the light, to bend the light. So light is coming and you put on a lens to be able to bend it. So basically, you're putting a system in place to bend the lights to a particular area. You want to focus it, just like your lens, when you design it to bend into the retina, either in front or behind, depending on your condition, so that you can see. because it's supposed to focus on the retina. If previously it's going behind it, you bring it back. So in any of this, then that is less than the diameter. These are the keywords that we are using. You have the red lights, so way to bend, put in the very necessary that will help the light to bend. So these are the things that you're able to understand. And that's what they employ in opticals that we have. So basically, this is what we know. So measurement of lights are carried by great scientists, just able to know the speed of lights, how fast the lights can travel. Fast. Not how far, but how fast. So we're able to get all this. So now let's look at the wave and the reflection. So basically, if you want to talk about waves, how waves behave when they reflect, how do they behave when they reflect? They behave when they reflect. So the rules in a uniform medium, when you say uniform medium, so when you talk about through only air or through only glass, in a uniform medium, rays proceed in perfectly straight lines. They only change course when it hits a boundary. So either you are moving to a high dense area or less dense area, or enter a region with a different refractive index that trigger their reflection or refraction. Basically, that's what is happening. This is the model that we are going to use. This is the reality. Lights, the waves are going this way. So naturally, the reality is that light is a wave that we normally use. So now, these are the applications. Why do your headlights seem to vanish on a rainy night? Yes, those people who drive. Let's understand this. When you are driving, when it's raining, your headlights, does it look like you are not even seeing the road well? Does it look like that? Do you observe something like that?
Yes. So when you're driving and it's raining, you don't see it seems to see the road well.
Yes, that is what is happening. When you drive on a dry road and a wet road, you observe the difference. You observe the difference. So basically, what we have to take note of is that it's all about optical reflection. It's all about the reflection. It's basically refraction. The reflection that comes from the root, because your light is root, what's the reflection? So using this example, the dry root. So this one, it reflects and come back to your eye, and then you're able to see clearly, because it hits the dry land, come back to your eye to see clearly. But here, when you talk about the wet root, flat, and go back to the other cars, it doesn't come back to you. So the seeing become a bit difficult. That's what happens. So you talk about reflection. So light expand boundaries or reflects dimensional use. So now we look at this is one-dimensional waves. So this is a waves, the sine waves. So now the three-dimension, as we know. So we have the incident rays, the reflected rays. So the angle of incidence is equal to the angle of refraction. This is the law that we know of. So now, looking at this, as we all talk about, you have your incident angles, your normal, this is how you draw it, and then you have your angle of reflection. So angle of reflection is always equal to the angle of incidence. Both measure from the normal, not the floor. So you don't measure it from here. So angle of incidence does not measure from, but they all measure from the normal. So from here to here, from here to here. but not from a line to the floor. No, it's to the normal. So this is what we know already, and we have been using since. So this is how the mirror here. So the reflected rays, the incident rays, and the normal all lie perfectly planar. The light cannot twist out into the Z axis. So these are the law of reflection, that the reflected rays, the incident ray, and the normal, the three of them all lies the same plane. That's what is happening. So now, when you are moving on a smooth surface, what happens? So you see the reflection. So the power organization strictly maintained. So this is what you see, that this one stands on the surface and reflects. So this is what is happening because the reflected rays remain perfectly parallel to one another. So this parallel, they are perfectly parallel to one another. So they will not meet. The optical image of the source is preserved. This creates a mirror light finish. So they are parallel. So as they moves in parallel. But let's observe this. But you realize that this is a rough surface. We have a rough surface when there's an incident. The same being reflected in many different directions with the rays scattered. So the same rays moving in different directions. They are scattering. So this is what you see, the same rays moving in different directions. Same rays moving in different directions. So this is what happens when it's a rough surface. This is something that we had this idea from SHS. So when light ray hit a boundary between two media, parts of the light is reflected. So on a smooth mirror-like surface, all parallel incidence rays follow the same reflection law. So the reflected rays stay parallel. This is called specular reflection. On a rough surface, let's say the wall of paper, the local normal at different points in many directions, even though each tiny part still follow the law of reflection. The overall set of the reflected rays scattered in many directions. The diffuse reflection. So you could see in the diagram, the surface looks smooth for visible lights if bumps and irregulars are much smaller than the wavelength of the light. Otherwise, it's at rough and diffusely reflected. So this is what you need to get. So when the surface looks smooth, what does it mean? So for visible light, if the bumps and the irregularities are much lesser than the wavelength of the light. The law of refraction, as we know about the incident rays, what does it mean? Reflected rays, what does it mean? The normal, what does it mean? What is the law of refraction? What does the law says? And take note that all of them are measured from the normal. So now, the driving lesson. On a dry or rough road, light from your headlight undergoes diffuse reflection in many directions. So some light comes back to your eye and you see the road. But on a wet day, the thin layer of the water formed a smooth specular surface. Most of your light is reflected away from your car, making it harder to see the road clearly. Mirrors rely on clear reflection to preserve the direction relationship of rays, allowing you to see clear image of yourself or objects. So basically, trying to look at this in a picture form. So this is a road that you are traveling on. The asphalt intrinsically rough on the scale of light waves. When the headlight hits on the dry road, diffuse reflection scatters some of that illumination back toward the source, drastically improving the driver's visibility. So the light hits and moves. So this is that's what's happening. So it helps you to see a bit better than when it's rainy day. So we have rainy day, some of the water is on the surface of the road as you are driving. Instead of this coming back to your eyes, some of them deflected away from your eye. So that created that not to see too clearly when it's a rainy day. Basically, that's what you observe. Diffuse reflection, blur reflection. The rays are power. It hits and you move. It hits and you move. They don't meet anywhere. But solar, they started meeting and know that there's a problem. This is basic science that we know about. So when waves encounter boundaries, it reflects. So specular reflections occur on a smooth surface. So incident parallel rays yield parallel reflected rays, and the law of reflection applies. Diffuse reflection occur on a rough surface. The same law still holds microscopically, but the rays scatter, so they no longer appear parallel. The law of reflection is the angle of reflection equal the angle of incidence, and the incident ray, reflected ray, and the normal all lie in the same plane. These are the two laws that we know for reflection. This is the core of the wave and the reflection model used in geometric optics. So basically, so when you talk about waves and their refraction, so waves and their reflection, this session we are going to explain how the waves go refractions, how it bends, why Snell's laws hold. So there are two medium. We have the air, which have the refractive index 1. We have the next medium, which is glass, have the refractive index 1.5, 2. So the lights, the yellow lights, the that lights, and the cyan lights. These are the colors that you mix the primary colors to get primary. Able to mix this to get the colors. Have you mixed these colors before? You mix the primary colors to get secondary colors. Have you mixed them before? Is my people there?
Yes, sir.
When the light ray travels from one transparent medium to another, part of the light reflects and part transmits into the new medium. The transmitted ray bends at the boundary and is said to be refracted. This bending is what makes pencil look bent in a glass of water, or the straw appear shifted in a drink. So basically, reflection is what we are talking about. The incident ray, reflected rays, the refracted rays all lie in the same plane, and the angle of refraction depends on the angle of incidence. So basically, This is what the law is saying. Look at this. So the incident rays is coming, and the reflected rays, and refraction okay. But I see that they all lie in the same plane. This is a coplanar. This is what they have. They all lie in the same plane. This is the plane that they have. So basically, the definition is what it's trying to depict. Should draw it. This is how it looks like. This is the incident rays, refracted rays. This is your normal. And this is the refraction, refracted rays. Instead of to go straight, it bend towards the normal. That is what we know about. So in this case, you add the velocity, each of them with their velocity, because in this case, rather when you are moving, your velocity reduces. So this is what you are relating to, the angle and their various velocity. So if the light go from faster to slower, that is from air to glass, you know that the first velocity will be higher. When you're moving fast, your velocity is high. So it will be higher. So this is what we have. So the angle of the second one will be low. Can you picture it? When you're moving from less dense to high dense land, the angle of the second one will be less than the first one, because the rays bend towards the normal. If light goes from slow to faster, that's glass to air. So the first velocity will be slow and the second velocity will be high. So the second one will be higher than the first one. And that means the first angle will be greater than the second angle will be greater than the first angle. The rays bend away from the normal. This is just the deduction from what you have. So this is what we are talking about. So this one, the first one, we move from here to this side. So this angle will be bigger than this one. The first angle here will be bigger than this one. Definitely. That is what is happening. This is what we're talking about. So if it moves toward this, the angle will never be equal. But this one will be smaller than that. So the ray path is reversible if the light will reverse direction. It follows the same line backward with the same angle of incident and refraction. So while light slow in a material, why is low in a material? So in a vacuum, light travel at 3 10 raised to the power 8 meters per second. That's what you know. In a medium, let's talk about the glass. The speed drop to about 2.0. Instead of 3, it dropped to 2.0. 10 raised to the power 8 meters per second. Why? Because the light is absorbed and re-emitted by atoms or the electrons along its paths, which delay the average speed through the material. Does it make sense to you?
Yes, sir.
Hello? Hello? Are you here? Hello?
Hello, sir.
Can you hear me?
Yes, sir, I can hear you, sir.
Yes, we can hear you, sir.
Hey, and I'm shouting and nobody's responding.
Yeah, sorry, we were here.
Tell me why light flow in a material. When the light is passing through a dense material, why does it slow down?
Yeah, because the light has been absorbed by the material.
Yo, when I ask you, I hope that you explain. So when a light exits the medium back into the air, it instantly returns to speed because the absorption re-emission process stops. This is very different from mechanical objects like bullets, which permanently loses energy while passing through barrier. So bullet, when it passes through barriers, they lose its energy. Like you use a bullet to hit a tree. It may go to a point, it may not come out if all the energy is finished, depending on how thick is the tree. But if it is to pass through, but the speed will reduce. The speed will drastically reduce. But the light is not like that. If it passed through the high density medium and then it's out, it still pick its energy again and continue. It doesn't lose the energy to the medium that it's passing through. It can pick it up to the next medium. But when you're in the first one, you share it so it reduces, but as soon as it's out from that medium, the energy is back and can travel at the same speed. But this is not the same thing when it comes to mechanical objects. Just like when we are trying to push our barrel, that's making noise. One side of the barrel slows down on the glass, while the other side keeps rolling fast on the concrete. The barrel pivots and change direction, mimicking refraction. So the things about refraction, refractive index. So refractive index, we talk about the speed of the light and the speed of the light in a vacuum, the speed of the light in the medium, and the speed of the light in a vacuum. These are the two things that you use to check the refractive index of a material. So the refractive, the C is the speed of light in a vacuum. And the V is also a speed of light, but in the medium that is passing through. And mostly rather that the speed of light in the medium is lesser than the speed of light in the vacuum. So that's why we normally have the refractive index greater than 1. That's why I have the refractive index greater than 1. The vacuum, if it's a vacuum, the refractive index should be equal to 1. So this is what notes that you need to observe. So basically you see the vacuum side, the vacuum, and the dense medium. When it's a vacuum, the N is equal to 1, and the material and the vacuum are equal. The velocity in the material and the velocity in the vacuum should be equal. By here, the N should be greater than 1, and the velocity in the material is less than the vacuum. That is why it is when you get it in material, depending on the material that you are using. So light moves from one medium to another. The frequency stays constant, but the wavelength change. The frequency stays constant, but the wavelength change. So when the V decreases, the lambda also decreases to keep the frequency the same. So that's what when the velocity decrease, the lambda also decrease. just to keep the velocity the same, the frequency the same. The wavelength in the medium with the refractive index. So the medium, so we have the lambda over the refractive index. So for when the refractive index is greater than 1, and then the medium is less than, the light has a shorter wavelength inside the medium. So this is what is happening. So you observe that shorter wavelength in the medium. So we know the Snell's law. Using the indices of refraction, we rewrite the Snell's basic refraction equation as. So this is the mathematical expression of the wave under refraction model. This is what we have seen earlier on. Well, what we are trying to look at is how you're able to balance this. How you're able to balance the refractive index and the angle. How do you balance it? To maintain the mathematical equality across the boundary, the optical density increases, the angle of light rays must correspondingly decrease. So as soon as you enter into the dense medium, the angle will decrease, will also reduce. So that's what happens. So you're able to balance the scale. So you're able to have your scales balanced. That's what happens. So when you see here, low refractive index to high refractive index. Low refractive index, so we are from here to this side. This one becomes lower. The 2 is less than this one, because the angle here, this angle will be greater than this. But when you're from high to a low, so rather this angle is lower and this one will become bigger. So this is how it works. So depending on the medium that you are traveling, that is what is happening. So if there is from A to B, the A to B, follow the refraction law, the ray sent from point B to A will trace the exact same physical path in the reverse. So this one comes like this. When I reverse it, we trace it back. So this is what's called the inverse, or the optical path through the refractive index. Oh, so this is what happens. This one comes, can trace it back. So this one, the physical path in reverse. So you can easily go through the same procedure. That's what happened. A wavelength comprised inside a dense medium where the frequency remain completely constant. The frequency remain still constant. So this is your lambda, the wavelength. This is your lambda, this is your wavelength, the velocity. So frequency is constant across the boundary. So either from less or high, the frequency will be constant. They will compensate for it. There is no energy parallax. When the speed decreases, the physical wavelength must compress to maintain these constants. So more compress to maintain the constants. So we have the medium wavelengths that we have. So the formula that's used to get it. So we have the wavelength of this. I put this here to be able to get what you are looking for. Frequency is always constant. The same models, the wave sound. So this model can be applied in sound, seismic waves. What are seismic waves? Give me an example of seismic waves. Hello? Hello?
Hello, sir.
Yeah, seismic waves, any example?
Earthquake.
Great, that's true. Earthquake. Earthquake, that's true. So all these principles apply in all water waves. So basically the angle. So these are the formulas that you are using. So if you have the first angle to be 30, the refractive index to be 1, the second refractive index is 1.52. So now you can use the Snell's law to find the second angle. So you should be able to use the formula when question is asked. So you should be able to use the formula when the question is asked. So you know the V2 is equal to N2 and 1 equal to this to find the speed and wave in the glass. So any of these questions, any of this law could be used in the calculation. So try and master these equations, able to understand it. That will be fine. The first angle. So basically what is happening with the phase 1, these are the empty space. See how you find our lambda. So it's the successive crest. So this from here to here, it gives you your lambda. But when you have the glass here, as the light passes through, see this kind of collision. So to lose the energy, but there are a lot of collision that is happening here. So there's repeated absorption, re-emission, delay the journey. So this is what lower the overall average speeds and compressing the wavelengths. So this is what is happening. So that you are moving from air. So you enter into a high dense medium. What basically is happening is that there's repeated absorption and repeated re-emission. Get absorbed, re-emit, get absorbed, re-emit, get absorbed, re-emit, until you are out. So you have fully your wavelength to move. So the speeds are retained and the wavelength expands. This is how light behaves. This is different from the mechanical. We talk about the bullets. Bullets will dissipate its energy here, and then you will not see it when it's out. That force will not come. But light, after that, the force is back. The energy is back that you used to travel. Can never reduce it. You're able to absorb it, and you have to re-emit. You absorb, re-emit, reabsorb, emit. It delays, but at the end, you go through the process without any actual hindrance. That is what the process has been. That is what lowers. That is a nice question. And believing that you can explain to my satisfaction. So talking about what is refraction, what is the Snell's law, the refractive index, all these are things that you should be able to take away, able to get the concepts, and able to use them. And that is what we have to take note of. Dispersion, how the dispersions occur. So how these lights burn by different amount. Because the index of the refraction of a material depends on the wavelength. So if I ask the questions, why different colors of lights burn by different amounts? So the refractive index of the material depends on the wavelengths. The refractive index of a material depends on the wavelengths. That's why different colors of light bend by different amounts. So what is dispersion? What it is? So the refractive index is not the same for all lights. The refractive index is never the same for all the lights. It changes with the wavelength because each light different wavelength. So most of the time, the refractive index decreases as the wavelength increase. Most of the time, you observe that the refractive index decreases as the wavelength increases. So looking at the violent lights, it has a shorter wavelength but higher frequency. And rather, it has a larger refractive index and reflects more. So when you look at red lights, it has longer wavelengths, has a smaller refractive index, and refracts less. But the red lights, a lot of energy that we know of. So because of the Snell's law, each color refracts at a slightly different angle, so the beam of white light can be spread out into its component colors. This spreading is called dispersion. So what is dispersion? The spreading out of the light into its colors. Dispersion. When a white light, as we know, white light contains all the visible wavelengths, enters a glass prism, each color experiences a slightly different refraction angle. The colors emerge separated, forming the visible spectrum. In order of decreasing the wavelength, so this is the order: red, orange, yellow, green, blue, and violet. Newton shows that each color has its own characteristic angle of deviation. This is what it shows. And that the same color can be recombined back into a white light by a second prism lens. This is what it's talking about. So this is the recombination using the same lens. So this is the separation. So you're able to separate the various colors from here, you're able to have your visible spectrum, and this can be recombined. So these are recombinations. So you get it back. So this is what Newton is talking about. So how rainbows form, how they form. The rainbow is the most vivid natural example of dispersion. So if you're talking about examples, you cannot run away. Rainbows shows what dispersion is about. The ray of sunlight enter a spherical raindrop. So the sunlight enter the raindrop. What happens? There is refraction. Reflect at the front surface. So dispersion begin. So the violet bends more than the red lights. Why? Hello?
Hi.
Hello?
Hello.
Yeah, so in a rainbow formation, refraction occur, but we realize that the colors, different colors in the rainbow. So what is happening is that when the dispersion begins, the violet bend more than red. Why? Why the violet color bend more than the red color? The bending depend on what? Depend on the wavelength. Yaira,
Hello, sir.
all right, Yaira is there now. I know you to be running away. Today you have not run away. So the light reflects from the back surface of the raindrop. But what you know that the reflection itself is not dispersive. Refracts again. So first refraction, and refract again. As the leaves the drop, dispersion increase. So basically, this is what is happening. So this is the present. The raindrop becomes very spherical. So the sun passes through this raindrop, this spherical object. So this is what is happening. First, the refraction. So the sunlight entered the till to disperse. So the second, the reflection occur. The light bounce off the back of the interior. So the third one, another refraction occur. The light exits, bending the second time, widening the color separation. So that is where you got the dispersion, the distinct colors which travel back towards the observer. So this is how the rainbows occur. These are the stages, the three stages, how it occurs. The first one, the refraction, the sunlight enters and immediately disperses into colors. Second, there is a reflection. The light bounces off the back interior wall of the sphere. And another reflection also occurs, as we can see from the first one. So that's why we see the violence manifest. So for the primary rainbow, the most intense, so we have the secondary and primary when the rainbows occur. So red light return at an angle of 42 from the original sunbeam direction. So you have the violet light return at the angle of 40. So this is the red lines and the violet, as I've mentioned earlier. So an observer between the sun and the rain sees the red from the raindrop higher in the sky. So the violet from the lower drops. So mostly when you see the rainbow colors, you see where you see the red and where you see the violet. Observe clearly and you see this difference. The result is a color pale with red on the outside and violet on the inside. So this is the red inside and this is the violet color outside. These are the angles that we see. The violet and red exits the rainbow to distance. So this was the violet has a shorter wavelength. The question that I asked, violet has a shorter wavelength. It experiences maximum deviation. Red, with its longer wavelengths, experience minimum deviation. Yes. I'm getting some exam questions. So see the violet outside, the red is inside. So these are the angles. So this is what you see. You are the observer that you see the rainbow colors. So it's the secondary rainbows. The secondary rainbows arise when the light make two internal reflection. So we had that two that happens. But first one is only one. The refraction is two. But here the refraction is going to be inside the raindrop before exiting. This is called the colors to be reversed. So the violet on the outside and the red in the inside. So when the reflection is two times, it change the arrangement. The violet go outside, the red come inside. More light is lost at each reflection. So the secondary power is fainter than the primary. So you see that the one looks very faint. So this is how the primary ones, and this is the secondary. So this is how the colors looks. See, so this is how they are. When the light reflects twice inside the spherical droplet, the exit geometry fundamentally change. The additional pollution causes two distinct phenomena. Here you see the insides are red. Here you see the insides are violent. So those are the changes that have occurred, depending on which one that is winning. So lights, internal reflection produce higher order of rainbows, but their intensity is very low, so they are sort of seen in nature. So dispersion is the separation of white light into colors, because the refractive index of the material depend on the wavelength. That's the key word. Violet bend more than red because the refractive index is larger but a shorter wavelength, so different colors follow different paths. Prism, spectra, and rainbows are classic examples. The prism spread white light. Rainbow form when the sunlight is refracted, dispersed, reflected, refracted again in a raindrops. Wow. Low dispersion material like fused quartz are preferred when you want all colors to focus almost identically as in the camera. Total internal reflection. This session explains total internal reflection and how it enables fiber optics applications. So this is the rule for total internal reflection. Total internal reflection is only possible when the light attempts to travel from higher refractive index into significantly lower refractive index. So that's the first one that you need to take note of. So the total internal reflection occurs when the light travels from the medium to this. So the angle of incidence increase. So this is what I want to take note of here. The N1 refractive index here, the N2 is here. So you realize that the angle of incidence is narrow. This is the angle of incidence. It's very narrow. The angle of incidence is very narrow. So we see that the light escape. So it becomes bigger. The escape here, the angle here becomes bigger. So now, this is the breaking points. So look at this. So as the incident ray hits the angle at 90, the light hit the exact critical angle. So we talk about the 90. The exit rays run entire parallel. So you see that how it's moving on this thing. That makes this from the normal to the ray here is 90. So when it hits, and then it hit the critical angle, see that it travel parallel. This is the break point. When you talk about internal reflection, this is what is the pinpoints of the whole thing. So the angle from the normal to the boundary will give you 90. That is what we call about the critical angle. The critical angle, the critical angle. So now the trap. So what happened is that it will not go into the next medium. These are two medium. So high dense medium moving to less dense. High dense moving to less dense. So what happened is that it will not go to the less dense. It gets reflected back. So when you are moving, instead of it to go out, it won't go out, it's reflected back. So the energy is conserved. When you talk of total internal reflection, the energy is conserved because the rays entering at a small angle and hits. So it will not leave the medium that it is. It will not leave. Instead, it will reflect back. This is what's happening, the trap. So this is what makes it very unique. So this is what happens in the fiber optic cables. So that's why we're able to carry the information, can travel far because it's not dissipated, it's not lost. It will become the same information that you are using. So this is the angle that you're able to create that they use in the fiber optic cables that help us to transmit informations without distortion. This is what's happening. This is a basic theory behind fiber optic cables, total internal reflection. This is what happens. So you have been given a question, the refracting depth for water and that of the air. Calculate the critical angle. Show you to calculate the critical angle, the formula that we have, and the total internal reflection. So this is supposed to be and then why the diamond sparkle that we see. So diamond has a very high index of refraction. So its critical angle with air is about 24 degrees. Ray meeting the surface at an angle greater than this are trapped. So when it's greater than that, it gets trapped, do not leave by many internal reflection, produces sparkles and strong dispersion of the colors. That's why you see it's sparkling. So when you enter, you get trapped. So you're able to see those kind of reflection that comes with them. That basically what you observe in fiber optic cables, the cloudings and the core, inside and the core. The fiber optic cable use total internal reflection. The lights along this glassy fiber around the curve. So the fiber consists of the transparent core with the index number and the clouding is slightly lower. So that it's lower than the inside. So that's total internal reflections occur within the fiber optic cables. That's why you carry the information without any distortion. Basically, fiber optic cables, that's what we use in our communication lines. When you go to medicines and imaging, that is what we use, endoscopy and those. So basically, it has been a great procedures that we use in everything. So fiber optic cables use the law of total internal reflections to be able to reserve so that there will not be, nothing is lost, the energy is conserved in that process. Moving from a high dense medium will never escape. It's maintained in that regard. So basically, this is what brought us to the end of today's lesson and to the end of the semester. We'll be meeting next week face to face according to our timetable. And then when we meet face to face, we'll try to look at, we'll conduct our midterm. So I'm expecting everybody to be there. I'm not expecting any excuse from anybody. the reason why he or she may not come, because it's very crucial. I expect you to come to the class. Let's have our mission. The first quiz that we wrote, some people were not there. So I'm expecting this one that's course rep, talk to everybody and let everybody be aware. We should plan ahead, and we are not accepting any excuse. It will be an opportunity cost. You pick one. You choose to go and make money, or you choose to come and get your certificates. So that's what is going to happen next week, God willing. We need to get there early enough so that we can use the time after the quiz. We can interact and explain some few things that we didn't get well. So that is my comments. Anything? We have 1 or 2 minutes more for our time to be up. I'm listening to you guys. Is somebody there?
Yes, we are here.
All right. It seems nobody's having an opinion, so we are ending today's class. See you next week. Keep safe.
Yes, sir. Thank you very much, sir.
All right.
Enjoy your weekend, sir.
Yes, I'm so better another one. Yes, face. Oh yeah, yeah. That GPT.